So ETABS basically dedicates itself to building system analysis and design. Now, in this 4 day session, we will see how to model, how to analyze, how to design, and how to interpret the results of the software. So today's session, I just want to know one more thing. Has anyone used the software before?
So,
Maybe in their college days, something like that.
so Dr. Harish BA is well versed with the
Okay,
software.
okay,
Uh,
okay,
he is the faculty member who is handling this module.
okay, okay, okay,
Then Aishwarya, yes, she's an PG student as well as an instructor in our college.
okay,
She knows little bit how to use this.
okay,
That's it from my end.
okay. So I will start from the basics. And in today's session, we will explore the modeling capabilities as well as we will also see some load applications and share the screen. So when you open the software, ETABS, you will get a window of this format. Here you will get all the latest news and the releases from CSI America. And in the left hand side, you will see the recent models that you have been working on. So that will be displayed. And you will get an icon for opening a new model or opening an existing model. And the menus that are displayed here, these are more or less self-explanatory. We will see that one by one along the as we move forward in this session. And there are some ribbons, toolbar ribbons at the top and at the left. So in the left, we basically have the drawing toolbar available with us and the selection toolbars. And in the top ribbon, we have some, you know, uh, file modification options like open, save, and then we can traverse through the different views like 3D plan elevation. And these are some of the post-processing uh, icons that are available. So when you start the model, we need to go to File and we'll create a new model. Now the program will ask us to define the unit systems and select the region in which we are working. So we have metric SI and the region will be Indian. And the appropriate steel and concrete design codes also need to be selected from this drop-down list. Now, once you press OK, the program will ask us to define a grid system and a story system. So grids basically are used to locate the different structural objects in a model. And uh, these grids will be for the horizontal plane. And in the vertical direction, we have the story system. So this is similar to our when you visualize a building will have a plan view and will have different stories. So just to uh, make it similar to a building system, this sort of a uh, template is used. to identify the structural objects in the model. Now, when I talk about structural objects, uh, as we all know, ETABS is a finite element based software. But while modeling or while working on the software, you need to work on the object level. Object in the sense, we have columns, we have beams, we have floors, we have walls. So these are the objects. Uh, so we need to model the objects and we will need to analyze and design them. Now in the background, there is an FEM solver that takes care of the analysis. We do not need to uh, go too much deep into the FEM aspect. We will limit ourselves to the object level. Okay, so a uniform now for the grids, there is a provision for having x say a four number of grids along the x direction and say four number of grids along the y direction. And here you need to give the spacing for these grids. So let us say we take grid spacing of 6 meters by 6 meters. And then for the stories, we can give here the number of stories for the building. So the first story or the bottom story basically refers to the founding level of the building. So if you have say a G plus 3 building, so you will be getting 5 number of stories, including the foundation level. And the bottom story height will be nothing but the depth of foundation plus your plinth height. So in this case, we are doing a G plus 3 building with a foundation. So we give the number of stories as 5. And the typical story height is 3 meters. So in the first case, I'm just going by making a very simple building model. And the template will be a grid only. Now, when I press OK, you'll get a plan view in one of the windows, and you will get a 3D view in the window on the right hand side. You can see now your grids are having a spacing of 6 meters each. And there are 4 number of grids in both the X and the Y direction. And you are having a bottom story, which is for the foundation. Then you have the ground floor. Then you have 3 number of floors. Now the first step, when we create a grid system, the first step in the model would be to define the material properties that will be used. So if you are doing an RCC building, we will define the concrete and we need to define the rebar material. So we'll add a new material, and from the region will be India, and the material type will be concrete. Now, if we select the Indian standard as per IS 456, whatever grades of concrete are defined in IS 456, those will be available. You can select any one of these grades. And in this material property data form, you will get the physical and the you'll get the physical properties that need to be used, that will be used in the model, like the weight per unit volume, then the mass per unit volume, and then the modulus of elasticity, which is 5,000 under root FCK, that will be calculated and it will be automatically taken. Then the Poisson's ratio, then coefficient of thermal expansion. So if you're doing a temperature analysis, this will be used, and the shear modulus from the Poisson's ratio and the modulus of elasticity. Now in the design property data form, you will get the concrete cube compressive strength, which is 25 MPa. Next, we will add the rebar. So here again, the material properties are taken up by the program. And in the design property data, you will get the yield strength and the ultimate tensile strength. So if you're satisfied with the data that is being used by the program, you can press OK and define the materials. Okay. Next step would be to define the structural objects one by one. So firstly, we will define the vertical objects, that is the columns. So we'll add a new property. And there are various shapes available to us for defining the concrete sections. If these shapes are not as per the project requirement, then there is also a provision of a section designer, which can be used to create arbitrary shapes, or even you can also use non-prismatic sections in case of tapered elements. We'll go in detail about these as well. So the first model, let us keep it basic. We'll have a rectangular section. Say we have a column section of 300 by 500, and the material will be M25. Now here in the section dimensions, you need to provide the depth and the width of the section. Now there is the provision of property modifiers here as well. That we'll see later on. Next is the reinforcement. Now in the reinforcement tab, you basically need to tell the program that the concrete section that we are defining is a beam or a column, right? So the design type, there are two design types available. One is PM2 M3 and the other is M3 design. So PM2 M3, as you can see, there are three types of forces. One is an axial force and the other two are the bending moments. So if the design type is an interactive design type like this is a column. And if it is M3 design only, then it will be a beam. Right? There is, you can see M2 and M3. Now, what are these? So M2 and M2 and 3 is nothing but the local axis of the member. You can see in the image of the cross section. You can see in the image there's an axis of 2, green color axis by the name of 2, and a blue color axis going by the name of 3. So these are the local axis of the uh, frame section. And your local axis 1 will be perpendicular to the screen, and that will be in red. So that is currently not visible in this form. We can view it in the 3D. So PM2 M3 basically means the axial force along the member and the bending moment about your local axis 2 and local axis 3. So now how to visualize the directions? This uses the right hand thumb rule. If you point your thumb upwards, that will be the direction of the local axis, and the remaining fingers, when they curl up, that will be the direction of the bending moment. So that is how you can visualize the direction of the bending moment uh, using the local axis. So for this particular section, this is a column. So our design type will be PM2 M3 design, and the longitudinal bars, we need to select the rebar material for the longitudinal bars and the confinement bars. So for the longitudinal bars, this will be HYSD 500, and confinement, we can keep it as 415. Okay, so you can also change the pattern of the reinforcement. You can have a rectangular configuration. You can also have a circular configuration. So depending on the column shape, you can decide on the reinforcement configuration. Now, if you have a circular configuration, then your then the confinement bars can also be a spiral. So your spiral also gets activated. Now in the check design, here your reinforcement needs to be checked or designed. So in our case, we will be designing the reinforcement. We will use this particular form. Now here for the design, you need to give some data about the rebar arrangement. So the program creates interaction surfaces when it carries out the column design. So you need to give the appropriate data. So you can mention here the clear cover for the confinement bars. So here your clear cover will actually be is for the confinement bars. So whatever is your effective cover, you need to uh, subtract the rebar diameter and the confinement diameter and give the clear cover. Now number of longitudinal bars along 3 direction face and number of longitudinal bars along 2 direction face. So along 2 direction face means the edge of the column that is parallel to your local axis 2. So there are 5 number of rebars here. And for the shorter direction, which is parallel to your local axis 3, you can give the number of rebars in this particular form. Okay, then you have the confinement bar size and your number of ties. So this can be kept as default. Next, we will add a beam section. So say a beam section having width of 300 and depth of 450, and the material will be M25. Now we'll go to the reinforcement tab. Here we will change it to M3 design only. And here you need to give the cover to the longitudinal rebar group centroid. Okay, so currently we won't, when you're doing a design or a linear analysis, you do not need to provide any reinforcement area overrides. So you can see now the rebars that were being displayed for a column section, that has disappeared. You can identify a beam or a column section when you just see the cross section. A beam will not have any rebars. So we have now defined the beam and the column objects. We will now add these beam objects and the column objects in the model. So there is this drawing toolbar ribbon in the left hand side, and there is an eye-shaped icon which is used for uh, drawing the columns. Now here you need to select the property from the drop-down list, that is C300 by 500. Now you can just snap this cursor to the grid intersections, and you can just left click and your column object will be added. Or you can simply make a window, can drag your cursor by left clicking and create a window and add these structural objects. Right? You can change the orientation of the columns by using the angle, by specifying the angle of the local axis in this menu. I'll turn on this bounding plane. Yeah, then it will be visible. So you can see we are working on the uh, story 5, that is level 14 meters. And in the 3D view, you will get you'll get a bounding plane that is displaying the level that we're currently working on. Okay, now we will add the beam objects. So the quick draw beam icon can be used. We'll select the property, that is B300 by 450. Now this beam object, you can see the cursor will snap automatically to the grid lines, and you can simply left click and add the beam objects. Or similar to the column, you can make a window by dragging the cursor from the left to the right. Okay. Now for the other floors, you can simply select these objects that we have added, and you can use the replicate command in the edit menu to create the structural objects in all the other floors. Okay, now you can use the plan view to view the structural objects in the different plans or in the different levels. Right. So you can remove the beams from the base. Next on, we can define the slab sections. Say S for 150. And the slab material will be M25. And modeling type, we will use the membrane. And here we will mention the thickness. Now we will use the draw rectangular floor icon, which is this rectangular shape icon. And from the drop-down list, we will select the slab section that we have defined, that is S150. Now we can simply, left click on this point here and drag it to the opposite corner and leave it. So you can add the floor object in this pattern, and you can replicate it to the other stories as well. You can use the drop down. You can use the arrow up and arrow down icons to move or scroll through the uh, plan views. Now you can see that the the geometry has been created for this model. Now we will move on to the load application. So what happens is in ETABS, by default, two load patterns are created. So what happens is you need to The process of load application in ETABS is that you have load patterns. So you need to define your load patterns in this particular form and then apply them individually. So by default, you have a dead and the live load pattern that is created by the program. And your dead load pattern has a self-weight multiplier of 1. So what that means is whatever structural objects we are adding in the model, the self-weight will be considered in this particular load pattern. Now, if you say you need to add some other superimposed dead loads, then you can select from the type a super dead load pattern, which will have a 0 self-weight multiplier. You can define, say, super imposed. Now you can select the, okay, so now we have defined one dead load pattern, which is for the self-weight. We have a super dead, uh, load pattern of the name superimposed. That will be for say the brickwork loads or whatever loads due to finishes are available, that we can use that particular load pattern. And we have the live load, right? So we will see one by one how we can assign the different loads. Say for brickwork loads. Brickwork loads are nothing but line loads or frame loads that will be applied to the frame elements. So you can simply select the beams where you wish to apply the brickwork loads. Now, anything that needs to be assigned, we need to go to the assign menu. And in the assign menu, we will go to frame loads. Now here the load pattern will be superimposed that we had defined. Okay, now in this form, there is, load type. We have forces. We can have, apply uh, forces as well as moments. And the direction of load application will be gravity for whatever superimposed dead loads are there. Gravity is here nothing but the negative z axis. Now in ETABS, your z axis is the vertical axis and x and y, these are the planar axis or the horizontal axis. So gravity direction basically means it is the negative z direction. And you have you can apply either trapezoidal loads or you can apply uniform load. So in the case of brick walls, we will be having a uniformly distributed load. You can see here in the 3D view that your frame loads have been applied. Okay. Next, we will apply the superimposed loads on the shell objects or the floor objects. So we'll apply shell loads and the type will be uniform. Say superimposed. Here we will apply the load as an uh, load load intensity or load per unit area, and the direction will be gravity again. Next, we will apply the live load as well for the floor object, say 3 kilonewton per meter square. Okay. Okay, now I will just run the analysis once and we can check how the uh, loads are getting distributed. Okay, so now what happens is when the analysis is run, there is a last analysis run log. You can check this analysis run log. You'll find that there is a modal analysis case that is running. So this modal analysis case is a default load case in ETABS always. Whenever we run the analysis, your even if you do not define any separate modal load case, this particular case will be automatically defined and it will run. So what is the basic objective of this? Uh, the program deliberately runs this to check if there are any, instabilities in the model or not. So if there is any instability in the model, it will be, you can see here, a basic stability check for the linear load case is carried out. And if there are, any negative eigenvalues, that will be reported, and uh, there will be a error message that there is an instability in the structure. Okay. Now you can see the display frame load assigns. Okay, now here you can check all the loading that is tributary to the frame object. You can press apply, and now you can see in this 3D view that the self weight of the slab or the floor object that is getting transferred to the tributary beams uh, as per the method described in IS 456. So dead load pattern is nothing but the self weight of the slab or the self weight of the individual beams and the columns. Next, you can check for the live as well. So you can see that we had, uh, drawn the entire, uh, we had drawn the slab on the entire floor of the building, but still the program will identify the edges uh, where the beams are intersecting and transfer the loads to the respective tributaries. Next, for the superimposed, so in the superimposed, there are also some brickwork loads along the edges, which was around 15 kilonewton per meter, and 4.5 kilonewton per meter is getting transferred to the edges. Hence, we are getting a 19.5 kilonewton intensity. Let me just increase the font size. Yeah, then it will be visible. So the load distribution is a triangular load distribution for the uh, loads on the slabs, and UDL for the brickwork loads. So this is how the program will transfer the forces to the adjacent uh, you know beams for the loads that are being applied on the slabs or the floor objects. Now you will get this kind of load distribution for the membrane objects that you define. So we actually define the slabs as a, sorry, that is S150. We defined it as a membrane. So in membrane, what happens is your slabs that you're modeling in this building will not have any out of plane stiffness. It will only possess in plane stiffness. Uh, Now, in plane stiffness is provided so that whenever we assign a diaphragm to the floor, it can, act as a diaphragm. Only reason being that, and for whatever vertical loads are coming to the floor object, that will get transferred as trapezoidal loads or triangular loads to the adjacent beams. I hope everyone is following.
Yes, sir. Yes, sir. You can continue.
Yeah. If there are any queries, you can always ask.
Okay.
Okay. So this was a very simple model where we just created the model and we had applied some vertical loads onto the model, and we had seen the load distribution. Okay, now I will take up another model where the grid spacing in this case was uniform grid spacing. Now we will have a model where the grid spacing is not uniform, right? Where the grid spacing is not uniform, and
Sir,
we will, yeah,
sorry for the interruption. Dr.
yes,
Harish has raised the question. Can you answer that question?
yeah, yeah, sure. Is it there in the chat box?
Yeah, yes. It's there in the chat box.
How can I assign a wall load only on specific portion of a beam in the software, especially when the wall does not extend along the full length of the beam? Okay, fine. So, okay. So let us say we have a beam in this case, right, where the wall is extending only up to say 4 meters. So this is a 6 meter beam. We have the wall only up to 4 meters. So we will go to the frame loads distributed, right? Now you can also make use of this trapezoidal loads form to create a UDL, right? Say you can use the either the relative distance or you can use the absolute distance, right? So distance 0 and say distance 4. Say I have a load of 50 and here again I have a load of 50. So you can apply your UDLs through the trapezoidal loads for making for assigning it only up to a certain distance. Okay. If the wall is resting directly on the slab instead of a beam, what is the correct method in software to model and assign the wall load so that it transfers accurately to the supporting members? Okay. So in that case, when you're having a wall on any one of these slabs, then it is preferable that you use a thin shell formulation. Instead of going by the membrane, you use a thin shell formulation. You can have this over here in the slab sections. So you can keep the modeling type as a thin shell, right? Now, in this case, say you have some load, some wall that is coming onto the slab. In that case, what you can do is you can draw a beam object of the property none. Right. Let us say there is a wall at the central panel in this particular slab. Right. So I will draw I'll turn on the snap options. So modeling in ETABS is very similar to using a CAD software. You have all these snapping options. Now, in this particular frame, which is having a property of none, you can apply the frame loads. So what happens is when you're having an out of plane, uh, when you're not having the out of plane stiffness, your uh, bending in the slab will govern the load distribution for your uh, in this case, the bending of the slab will govern the load distribution. So you need to define this as a uh, shell thin and draw a frame object of the uh, property none, and then run the analysis. So in that case, what will happen is your loads will get transferred uh, to your respective beams, but you will not be able to directly view it. So this is story 5. Superimpose. Can check the member force diagrams, and you can right click here. So your loads, your equivalent loads uh, due to the superimposed load pattern. You can see here at the center, there is an additional uh, load that is getting transferred to the particular beam due to the uh, brick wall load that has been applied over here. So to check that load transfer, you need to see it in the member force diagrams for that individual load case. Okay. Okay, so we will now move on to model 2, uh, where we will have a custom grid spacing, which is, a more practical scenario. In most of the buildings, we do not have uh, uniformly spaced grids. So the user should also be aware of how to use the custom grid form. So we have the grids parallel to the y-axis as the alphabetical grids, and we have the grids parallel to the x-axis as the numerical grids. Right. So let us say now here the grid spacing is can be given as either ordinates, or you can give them as uh, spacing. So when you are using the ordinates, you need to basically give the distance of the respective grids from the origin. So let us say we have grid B, which is at 6 meters from grid A. Then grid C is at 4.5 plus 6. So 4.5 meters is the spacing between grid B and C. Then we have grid D, which is at 3.5 meters from grid C. Then we have grid E, which is 4 meters from grid D. And lastly, we have a grid F, which is 5.5 meters from grid E. You can see here in this particular image that your grid spacing uh, is also getting updated. And now for the Y grid, let us also have 6 number of grids. And say grid 2 is at 4.5 meters from the origin. And grid 3 is 5.5 meters from grid 2. Grid 3 is 3.5 meters from, sorry, grid 4 is 3.5 meters from grid 3. And grid 5 is 6.5 meters from grid 4. And grid 6 is 4.8 meters from grid 5. Next, you can also use the custom story data form for creating uh, stories where the heights are different for individual stories. For example, if in a building, if there is a multi room or say a machine room, then the floor height can vary from the other floors. So here again, we will keep another story. Say story 1 or the bottom story is 2.5 meters. And the last story here is again, say 2.5 meters, which may be a multi room or a machine room. You can see here now your grid system has been created. Okay, now we will again carry out the same procedure. We'll create the grade of concrete that has to be used. Then we will create the rebar. Next, we will create the frame sections. This will be M3 design only. The rebars will disappear from the cross section. Next, we will define the slab sections. So we can create, multiple slab sections. Can keep this as membrane. Okay, now we will again start with quick draw columns. Now we will quick draw the beams. Next, we will draw the slabs. Say S150, we will use for say these regions where the slab dimensions are more. And for the remaining, we can use S125. Okay, now we will go to the load patterns. Here we will create a superimposed load pattern. And we will assign the shell loads. Say finishes. And then the live loads. Right. Next, for the wall loads, we will select the beams. Assign this will be superimposed. Right. Now, you can also use the replicate command to recreate the in fact, the loaded objects in all the floors. You can assign your uh, loads and whatever properties are there in one floor, and you can replicate them to all the other floors as well. So I'll select this and can use the replicate command, or you can use the shortcut, which is Control plus R, to create the geometry for all the other floors. Right. And say in the topmost floor, we have a Mumpty in this particular region. So we can omit the structure. And say we need to remove the loads that we had applied here, we can simply go to the distributed, and in the superimposed, we can make this 0 and replace the existing loads. So this is, yeah, this is the structure now. Move to the base and remove the shells that were added. Now for the Mumpty region, we can have another slab. And for the superimposed, we can keep it as 1.5. Okay. And now we will also see some more things, additional things, like addition of secondary beams, then how to, you know, provide uh, releases. And we will also see about, the insertion points of the various, beams. Say we have some, uh, we have a column. Okay, we'll see that directly. Now in the base, you can see by default, all the columns are having a hinged base. You can select from the coordinate specification any joint on the XY plane. And you can go to assign, joint, and restraints. You can convert it to fixed.
So sorry for interrupting. Can we have a
Yes.
break of 10 minutes?
Yeah, sure, sure,
Hmm?
sure, sure.
So we'll break and again we'll meet after 10 minutes.
Okay.
Fine. Sir, can we start the session?
Welcome back.
Right, sir. You can continue.
Yeah, so we were about to start uh, discussion on how to add secondary beams in our model. Uh, if you have used this software before, you can see there's an icon for quick draw secondary beams. Uh, we won't be using this particular icon for adding secondary beams for RCC structures. This can be very well used for a steel structure or a steel composite deck structure where there are multiple secondary beams with predefined spacing. This particular icon will work very well in that case. For RCC beams, what we will do is we will use the replicate command to add secondary beams. Right. So in this case, let us add some secondary beams in this particular panel, right? Between grid 4 and 5, which is at a distance of 2.5 meters from grid 4. So what we will do is we'll simply select this beam that is lying along grid 4, and we will use the replicate command. Shortcut is Control R, and we will replicate it by 2.5 meters along the y-axis. So our secondary beam will be added here. Similarly, you can also create secondary beams in some other panel in the same method. So you can use this even for your x-axis as well. Right. Now, if you wish to use the same section, that same section property, that is fine. Otherwise, you need to define a separate frame section for the secondary beams. So what you can do is you can create a copy of this property, say secondary beam, 250 by 450. Can select these beams here and assign the frame section property. So normally secondary beams are, kept in the regions where there are, some walls or, even sometimes to reduce the slab panel thickness. And they are normally moment released at both the ends. So we will select these secondary beams. And now moment releases are also a property of the frame object. So we need to assign that. We go to assign menu, frame, and it is under the releases or partial fixity. So the starting point of the member, we will release the torsion and the moments along local axis 2 and local axis 3. And at the end, we will release only the major and the minor moments and not the torsion. Torsion will not get released. Otherwise, there will be instability issues in the model. Now, assigning loads to the secondary members, it is similar to what we had done. Say there is a half wall in these portions. We can assign the loads in this pattern. Now you can see that we have added the member even after the slab has been, no, the slab has been added before, and we are adding the member after that. This will not create any issue. The load transfer will be proper. You can check it by just, simply running the analysis. Whenever you run the analysis, the program will ask you to save the model. Right. And in the 3D view, I will change the building view limits so that we can concentrate on story 1. So anything that has to be changed in the view, you need to go to the view menu, and here there is set building view limits. So in set building view limits, you can limit the portion of the building that you wish to view. So you can view a certain portion of the building, or you can keep it as show all. So the limits are being, displayed in this using these 4 blue colored dots for the plan. Here we will focus only on story 1 in the vertical plane. Right? You can see now that your secondary beams are also, bending. You can see the deformed shape from this particular icon, the show deformed shape icon. And change it to superimposed. And you can see that your beams are bending for the superimposed loads as well, even for the live loads. So they are participating in the gravity load distribution. As we are using a membrane, we can check the load distribution to these secondary beams. can change the font size from the graphics preferences for better viewing. So there was a 7.5 kilonewton UDL applied on these secondary beams, and the triangular loads from the adjacent, you know, from the adjacent slabs are getting transferred as well. Now, due to the addition of secondary beams in these panels, your load distribution will be primarily one way. Right. So you can define your membrane having a one-way load distribution, and you can instruct the program to also distribute the loads accordingly. So you have your uh, load distribution that the one-way load distribution will be happening along the y-axis in this case, and along the x-axis in this particular case, and along the y-axis in this case as well. Right. So what we will do is we need to now define a separate slab section, say S125, one way, and use the special one-way load distribution. Now what we will do is we will use the reshape object cursor that is available in the left hand ribbon. We will use this to remodel the slab that we had added. We are just changing the extents of these individual slabs. Now we will use the draw rectangular floor object and we'll select S125 one way. So this arrow here represents the direction of the load transfer. This will be a normal two-way slab. Now here the load transfer is not as per the requirements. We can simply select these slab objects and change the orientation of the uh, local axis. So we will go to assign shell local axis, and here we will rotate it by 90 degrees. So what happens here is your local axis 1, which is being shown in red, that will determine the direction of the load transfer for one-way slabs. So if you rotate the direction of the local axis 1, your load transfer directions will also change. Let us discuss a little bit more about the local access for the frame sections. So if you go to display, set display options, you can turn on the local access for your frames. Now here, your local axis one, you can see it runs through the longitudinal direction uh, of the beams as well as the columns. For the columns, it will be visible in the 3D view or in the elevation. Uh, Whenever you right click on any one of these uh, beam objects, there will be a geometry tab. Now in the geometry tab, there is an end I and an end J. So end I here represents the starting point of the member, and your end J, it represents the end point of the member. So your end I and end J, you can understand that by looking at the direction of the local axis. So here it is, running in this direction. So your member starts from here and it ends here. So this is how you can identify which is the starting point of the member and which is the end point of the member. This you should be aware of this while assigning releases or even insertion points in the model. Now, what is insertion point? I'll just give a brief understanding of what is an insertion point. So I think you are aware of how the beams and the columns are oriented or even how they are joined. So if you are in a plan view, if you are seeing a column like this and your beam is joining like this to your column, then there is an there's an offset from the centroid of the column object by some distance. So to model this in ETABS, you can use the insertion point. Now, if it lies within the minimum eccentricity as prescribed in the IS code, then you do not need to model the insertion points. Otherwise, you'll have to do it. So I'll turn off the local access just for once. You can check in the extruded view. So in the extruded view, you will get a 3D rendering of the structure. And you can see here that for, in the vertical direction, your mm, your beam and columns they are getting attached at the top center. And so is for the slabs. They will be attached, they will be joined, in fact, by the top center. So if you're having a This is not working. So say this is the cross section of the beam. Now in ETABS, your beam will be divided into various cardinal points. Cardinal points in the sense is the insertion point of your frame objects. So there is, the top and the bottom edge. So in the top, you have the top center. You have the, the top left and the top right. Similarly, at the center, you have center left, centroid, and the center right. And at the bottom, you have the bottom left, bottom center, and the bottom right. So you can join different frame objects through these cardinal points. And if you need to provide some offset, then these offsets will be provided from these cardinal points. We turn on the building view limits. You can also view the insertion points by right clicking on any one of these members. In this assignment, you can see here insertion point is CP, that is cardinal point at top center. And currently the joint offsets, they are none. There are no joint objects currently. As there is no, joint offset, it is the center lines of the beam and the columns, they are, matching. Okay. Now let us say we need to model a certain amount of, offset for this particular beam, where the beam will be, the edge of the beam will flush with the outer edge of this particular column. So you can select this beam and you can go to assign frame insertion point. Right. And the cardinal point will be your, as I just explained, you have, see, there are multiple cardinal points. You have the bottom left, bottom center, bottom right. Then you have the middle left, middle center, middle right, top left, top center, top right. Then you have the centroid and the shear center. So by default, the beam objects, they are modeled as they are inserted on the top center. And on the coordinates and the offset, you can provide the offsets either by using the local axis coordinate system or by using the global axis coordinate system. So in this case, we will provide an offset along the y-axis for both end I and end j. And in this case, our beam is 300 mm and the column here is 500 mm. So we will provide an offset of 100 mm, to flush this particular beam with this column. So this will be positive. And turn on the extruded view, and you can see here. Now, whenever you are providing, such an offset, you need to turn off this particular dialog, that is, do not transform frame stiffness for offsets from centroid for non-PT flows. So you need to turn this off so that the effect of this eccentricity is captured in the analysis. Okay, now we will run the analysis. For viewing the uh, member forces, you can go to display member force diagram. And here you can select the appropriate load case. Now, till now, whatever we had, defined and applied, those were load patterns. What the program does is it converts these load patterns into load cases and runs the analysis, and then uses them for creating the load combinations. So we will view, say, if you wish to view the moment diagrams for your dead load case. You can view them. Can turn on the show values at controlling stations. Then you will get the uh, maximum positive and the maximum negative bending moment values in the diagram. You can right click on any one of these beam objects, and you can see the equivalent loads that are being transferred to this particular beam object. So as you know, the dead load case consists only of the self weight. So your self weight of the beam will be there, and the self weight of this particular slab panel, the equivalent portion that will get transferred to the beam, that will get displayed here, and the end moments from the columns, and the reactions from the columns will also get displayed here. Then you can see the shear force diagram and the bending moment diagram, and your maximum values will get displayed at the right hand side, and your deflected shape and the deflection will also be shown here. You can scroll uh, this particular cursor to different points, and you can get the values. Otherwise, you can always show the max and check the maximum values of each of these items. Similarly, you can view the minor. So the first is major bending M3 and major V2, that is major shear or the vertical shear. You can view the minor shear and the minor moments as well. And the last is for the axial force and torsion on this particular member. Now here you can see one more thing, that is the end offset location. So end offset location for end I is taken as 0.15 and for end J is taken as 5.75. So what are these? These are nothing but the effect of the uh, the column rigidity being captured. So the bending moments that are being reported here is for the clear span and end I, which is the starting point of the member. Here we have a rigid zone of 0.15 meter, and at end J we have a rigid zone of 0.25 meters, which is being captured. You can see this particular, offset being captured by each and every member in the model. Uh, Even for the columns, you can go to the elevation view. And here also you can see that your bending moments are getting reported up to the bottom of the beam. So uh, the rigidity of the joints are being used to calculate the bending moment up to the face of these joints. Now, as we had noticed earlier that the beams are getting joined at the top center. Hence, there is no rigidity at the top, at the bottom of the column, and hence they are reported up to the beam top. User is also free to, to override these offsets that are being recognized by the program. We can we can tell the software to collect bending moments up to the, the full length of the member. That is also possible. We can, in that case, we need to unlock the model and we will select all the members here and we will go to assign frame end length offsets. So end length offsets are automatically collected from connectivity. You can select the define lengths and keep the length as 0. In that case, what will happen is uh, your bending moments and shear forces will be reported for the full member length. Okay, I will just reverse this to automatic from connectivity. You can see here at the individual joints how the uh, rigid zone is being captured. Now, in ETABS, we will see the individual design of the beams as well as the columns. So when your load cases are created, you can run the design directly. The program creates auto-generated load combinations that will be used for the design. So this particular icon here is for the concrete frame design. You can simply start the design check and your design will run. And your rebar quantity or your rebar areas will be reported for the individual beams and the columns. So you can see what happens is in the load combinations. Now, currently we have defined only the gravity loads, that is your dead and live loads. So the program has created two combinations. One is decon S1 and another is decon S2. So decon basically means default concrete. S is for strength and one is the number. So the first load combination will consist of your dead and superimposed loads with the scale factor of 1.5. And the next will also contain the live loads with the scale factor of 1.5. To view the beam reinforcements, it's better to view it in the plan view, and for the columns, you can view it in the elevation view by going to display design info and turn on the total longitudinal reinforcement. Now here you can see your rebar area is being reported at the top and as well as at the bottom. So they are reported at three particular stations. One is at the end I and the other is end J and the third is at the center. Now to arrive at these values, the program runs the design at uh, various locations along the length of the member. You can right click on this member and you can view here that the program runs the design. So this is the the combination, and the second column is for the station location. So you can see here the program will run it. It has run the design in this member for various sections up to the end, that is 5.75 NJ, and your top and bottom steel has been computed at these various locations, and the maximums are being reported. So what happens behind the screen, behind the screen is the program will create an envelope case and report these values. You can check the details for the design. So the first report is for the summary, the beam section design summary. So the program runs carries out the design combining 456 and 13920. However, in this particular model, there is no lateral loads. It is only a gravity design. So the relevant clauses will not be, the relevant clauses of 13920 will not be check. So here the maximum factored forces are captured. Then the design is carried out for both bending, shear, as well as torsion. Now, in the flexural details, you will see the details of the flexural design. So, similar to the summary page, the first few rows will consist of the section sizes, the covers, then the materials of the material properties, and then the flexural design. Similarly, there is a tab for the shear details. Here you will see the forces for shear design and the equivalent shear due to torsion will also be considered. And finally is the envelope. There are also diagrams available for the beam design, which will show an overall envelope of the forces and the rebar quantities. So this is the moment diagram envelope for both top and bottom. Then the longitudinal steel envelope, shear diagram envelope, shear stirrups envelope. Now shear stirrups are reported in mm square per meter. This is the torsion diagram. Sorry, there was, I think, some connection issue. Temporarily, we got disconnected. Yeah, so we were, discussing on interpretation of the uh, beam design results. Can you just tell me last time, when we just, got disconnected, where were we? Can you just tell me? Then I'll start from there.
You were explaining about the diagrams. What is
Yeah,
the bending?
diagrams.
Yeah,
Yeah,
bending moments, shear force.
yeah. So the in the design details form, there are diagrams available for the overall envelope. Like for the bending moment, both the top and the bottom. Then the longitudinal reinforcement envelope, which will, here the maximum will be reported at the bottom of the diagram. Similarly here as well, you can see the uh, maximum is being reported here. Then the shear force diagram, the shear reinforcement diagram in square per meter, and the values are being displayed here. And finally, the torsion diagram. Okay, now whatever we are viewing here in the form of a graphical user interface output, uh, the same things can be viewed in the form of tables as well. Okay, we will get to those tabular outputs maybe in the second or third session, where we can export those tables to Excel and create reports. Okay, now for the columns, here uh, the value of the longitudinal reinforcement will be reported along the length over here. The lines that are shown in purple, they represent the columns. Now here for the columns, your column design will be done for both the top and the bottom. And the maximum value will get reported over here. Right. Similar to our beam design, we have column design outputs as well. We can right click on any one of these columns. And you can see here that for the column, it is carrying out the design at 3 locations: top, bottom, and one at the center. Right. And there's an interaction surface that is being generated. So this is the interaction surface, and these are the coordinates. Then in the details, similar to our beam design report, you will get the the frame section details along with the cover material properties and the factors of safety. And here you will get the axial force and the biaxial moment design forces, and the minimum M2 and M3 is taken from the code. And then we have another factor, that is capital K factor, which is from the which is calculated from the appendix of IS 456 for a sway frame or a non-sway frame. The program actually internally calculates the Q factor for the model, and it will take up the appropriate K factor depending on whether the frame is a sway or a non-sway. So as you can see here that we do not have any lateral loads, so these particular checks are not carried out. And then there is a check for the slenderness. In the flexural details, So you can see here, there is no sway in the frame. Similarly, for the shear details, you can see how the shear design is carried out. Then the rest of the things like joint shear details and beam column capacity ratio, these will not be checked currently, as there are no lateral loads in the model. Okay. So I hope this is clear up till now. Uh, we will now see, uh, you know, two more things if time permits. Firstly, we will see how to, you know, how to create structural walls in the model or shear walls. And if time permits, we'll also see how we can model staircases in ETABS. So for structural walls, we need to define a wall section first of all. So that will be defined from the section properties, wall sections. Here we'll add a new property, say W300. And the wall material will be M25. Modeling type in this case will be a thin shell. There are several other ways also to uh, model a wall. But if you wish to capture the bending of the wall, then you need to model it using a thin shell. Okay, so now what we will do is I'll turn on the all stories option from this bottom right hand corner. Here we will select these columns at the outer periphery. We will remove these columns and we will add walls. And from the property, we'll select W300. Let's keep the 3D view active here. Then you can see how the walls are getting added. So now we will, try modeling a staircase in, one of these panels. I'll remove the slab from this region, and we will add a dog leg staircase uh, in this particular panel, which will move, say, somewhat like this. Now, to do so, we need to add a reference plane between our floor levels. Now, we should not add stories in between the floors. We should always add a reference plane. So we'll go to Edit, Stories and Grid Systems. Now here we will go to Modify Show Grid System. Here there is an option for reference planes. So the first reference plane will be at the mid height of your ground floor and first floor. So the Z ordinate will be 2.5, which is the bottom story height, plus 1.5. And the ID will be mid landing 1. Next, we'll keep mid landing 2 at 3 meters from the first mid landing. Now, when you go to the plan view, we'll see there are some reference planes that have been added at the at the middle of both these stories. Here you can add your mid landing slabs as well as beams. So we will also at the staircase, we will define a slab section for the staircase. Say SC staircase, and modeling type in this case will be a thin shell. Now staircases will be added to the building, but mainly to check the mode shapes and to capture the the effects of the staircase on the columns. The staircase design will not be carried out in ETABS. It is only there to study the the effect of the staircase on the structure. right? So in the 3D view, or in fact, you can work on the reference plane. We will add a mid-landing beam at this level and say the staircase mid-landing has a width of 1.5 meters. So I will add another beam here just for modeling purposes. And we'll right click on the screen and turn on the snap options, snapping to midpoints and perpendicular projection. Now we'll come back to story 1 from where the staircase will start. We will select this polygonal shaped icon for drawing the staircase. We'll select the SC175 slab. So we'll click on this joint, and next we will move up to the reference plane level. This will be the second joint. The midpoint will be the third, and we will go down and then right click to complete the staircase. You can see here that your staircase slab has been added. Now we'll come back to the plan view, and we will add the mid landing slab. I will create the other flight. We'll come back to the reference plane and complete the staircase. Okay. Now, for the staircase, you need to assign the loads for your steps. So whatever steps are there, the weight of the treads and the risers, they need to be assigned as shell loads. So you can assign that as a shell load, a uniform type shell load. We have 2.65 kilonewton per meter square. And this will also, you can also give the live loads, say 3 kilonewton. Now, what you can do is you can simply select the uh, staircase slabs and replicate it to all the other floors. Just remove this Mumty from here, and we can have the Mumty in this region. We'll just select these particular frame objects and we'll replicate it to the story file. Okay, you can now simply, draw another uh, slab object over here and add the multi-level slab. Okay, so I hope till now what we have done, it is clear to everyone. We can, have some queries if it is, if there are any.
So I have a query.
Yeah.
So is it not possible to design the slab thickness of the staircase in ETABS? The
Uh,
reinforcement and all?
no, 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 no.
So we have to do it manually again.
Yes, that has to be done manually.
So if I want to provide other types of staircases like open well staircase or spiral staircase, is it possible to model in ETABS again?
Uh, yeah, you can do that.
Okay.
You can do that. Uh, in that case, you will have to define the geometry, before you do the modeling. Like you can have, circular ramp type things. Spiral staircase, if it is, like a very small,
Okay.
spiral staircase, that I think, modeling, uh, will not be very feasible. If you
Okay.
have circular ramps or, circular shaped staircase, that you can model. You will also get the, the shell forces
Okay.
uh, from ETABS.
So
Then you can use that for design.
mainly then using ETABS, the staircases is only for the analysis purpose then.
Yes, only for the analysis. Like staircase can, impact your mode shapes, time
Yeah,
periods, and
yeah,
all
that
those
I can
things.
understand. Yeah.
So only for that. Yeah.
Okay. So one more thing. So the video what you recorded,
Yes.
please share it us.
Sure, sure. I'll share that.
Then do you have any study material so that we can self-learn certain things? Because in this limited 3 hours,
Yeah.
is there any standard handbook like materials you have prepared so that we can self-learn the things by reading those materials?
Uh, Actually, there are some manuals available in the documentation section.
Okay.
In the help button, when you go to documentation,
Okay.
there are, various manuals available.
Okay.
There is uh, analysis reference manual.
Okay.
So this reference manual is, uh, here it is showing only for ETABS, but it contains
Hmm.
the analysis manual also for SAP.
Okay.
Right? Like whatever objects or finite element you know uh, finite element elements are there that will be available here. In fact, even the load cases, load patterns, details about that are available in this particular manual.
So what you have just explained, all these steps are available in this manual so that we can
Uh,
read them.
okay, reading, I think in that case, uh, there is this steel frame, like there are individual examples also in this
Okay.
particular manual.
For example, just now you explained in multi-story building, you took an example. So step
Yeah.
by step, what we have to do, is there any standard manual like that? So that,
Oh, okay, okay. Actually, in like in ETABS, there is no continuous workflow.
okay,
It is actually to and fro.
okay,
The workflow is to and fro.
okay,
Like say your sometimes you need to go to the analysis, check the results, come back again. Okay, but your modeling procedure will
hmm,
remain the same.
yeah, okay,
Like whatever we have done up till now,
hmm,
that modeling procedure will remain the same for most
okay,
of the structures.
okay,
Like there are some edit commands available in this particular menu that I have not used in this model. For
okay,
RCC, whatever commands I have used, that will be adequate. When we
okay,
are doing steel buildings, then
okay,
we might have to go for extrude.
okay,
Okay, then you know these things have to be used depending on the structure.
okay.
So today's class was a basic class on
Yeah,
RCC model, right?
yeah, understood, understood.
Yeah.
Yeah,
So further reading material, I think you will get from this documentation section. Okay. Once our 4 days training session is over, then you can refer to
yeah.
those manuals.
And one more thing, sir, is it
Yeah.
enough 4 days training session? Can you cover the entire thing? What you want to express in this 4 days, or do you
Uh,
need some more time for that?
I
Is
I
it
think I think I will try my best to cover.
okay?
If anything is pending, we can always add some
Okay.
sessions. Like today, I went quite slowly. I went
Yeah,
very
yeah.
slowly so that people can get an understanding of the software. Uh, I think we will be able to cover. If
Okay, sir.
not, then we can arrange one more session.
Okay, sir. Fine, fine, fine.
Yeah,
Thank you.
yeah, yeah.
So I can share the videos, and again tomorrow at the same time we'll log in at 10 o'clock.
Yes, yes, sure, sure. So
Okay, thank you.
yeah, thank you. Tomorrow's session, we will see lateral loads.
Okay,
Okay, both static as well as dynamic.
okay,
And we'll also see wind load application. We'll
okay,
see shear wall design.
okay,
Okay, as well as whatever building frame design is there.
okay,
And maybe day after tomorrow, we will see slab design
okay.
and steel frame design.
So,
Okay, so slab design will be a short 1 hour session,
okay,
and steel design for the rest, like 2 hours, we'll focus on steel design.
okay. Then and in the last day, I think you'll be covering safe, right?
Yeah, safe. And some more advanced topics I'll cover. I'll cover pushover analysis as well.
Okay. Fine, fine, sir.
Okay.
Fine.
Yeah.
Right. So shall we end the meeting then?
Yeah, we can end now.
Okay.
Thank you for joining.
Thank you. Thank you very much.